So I will demonstrate that. Go to the PyCon 2015 link. These are all the installation instructions. Scroll, scroll, scroll. All the way at the bottom, my slides. And hopefully you can open those, and if you do, it should look like this. And I will now go into present mode. So I'll come around and see if I can help with environment issues. I'll also introduce Alex Dorsk, who is my very helpful volunteer teaching assistant for today. He can help you out with environment issues as well. And we'll start in earnest in about 3 or 4 minutes. Okay, I'm going to get started. One suggestion, if you are working on getting your environment set up, stop for now. I'm going to talk for about 15 minutes to introduce some things, then we will launch IPython. When we do that, we'll get back to fixing environment things, but if you are really concentrating on environment things and not listening, then when we start the hands-on portion of the program, you will have no idea what's going on. So listen up. All right, I'm Alan Downey. The workshop is Statistical Inference with Computational Methods. Obviously, if that's not what you wanted, this would be a good time to very quietly sneak out. I won't even look if you're sneaking out of the room. It'll be all right. Just a little bit of background on me. I teach at Olin College, which is a brand new engineering school. Well, it's 15 years old. It's in Needham, which is just outside of Boston, Massachusetts. And our mission is to fix engineering education. So we're doing a lot of new curriculum, a lot of new pedagogy. Here are a couple of projects the students have worked on. Brand new campus, and there's me teaching a class. Plan for today, we're going to talk about statistical inference. What I mean by that is looking at a sample from a population and estimating effect size, how big, anything that you think is going on, how big you think that effect is, quantifying how precise that estimate is, and doing hypothesis testing. And I'll explain what all of those things are as we go. Most of what I'm doing is based on 2 chapters from Think Stats. This is the 2nd edition that just came out about 6 months ago. It's published by O'Reilly if you want a hard copy. It's also available at thinkstats2.com, 2 for 2nd edition. And that's under a Creative Commons license, so you can download the PDF, you can make modified versions, you can translate into other languages. Some of what I'm talking about today is based on my blog, which is called Probably Overthinking It. I publish a lot of things about statistics and Bayesian statistics. This particular series you might enjoy. Last semester I taught a Bayesian statistics class. The students worked on projects. This semester I'm taking their reports and publishing them as articles in my blog. The one that just came out a week or so ago is the students who did a Bayesian analysis. They did survival analysis for the characters in Game of Thrones. So they're predicting who will survive the next 2 books and who won't. Of course, the other piece of that is predicting whether George R.R. Martin will survive the next 2 books. So we can do that. I've done that analysis. He has, according to the numbers that I've plugged in, I think he has a 75% chance of completing the next 2 books. The code that I'm going to be talking about is all at GitHub. Hopefully you've downloaded that. The links are in the notes that you've got. Again, we'll get the environment set up soon. So an interesting thing happened. I proposed this workshop for PyCon, and then a few weeks later, there was big news in the world of statistical inference. There was a journal in psychology that published a white paper that said, we will no longer allow papers, we will no longer publish papers that do conventional statistical inference. No p-values, no standard errors, no confidence intervals. We just want effect sizes, period. And this, of course, sent a lot of shockwaves through the people who do these kinds of things. This is an article in Nature that's about the journal. So it's not that Nature banned p-values. It's that they're writing about a relatively minor journal that banned p-values, which might have been strategic on their part because now everybody has heard of this journal. It also might have been strategic because people have been talking for a long time about the problems with how statistical inference gets done, and nothing ever happens. So I appreciate the fact that the journal shook things up and got people talking about this issue. What I want to do today is explain what the problem is that they are reacting to, and I'm going to make a recommendation about what we should do going forward for both science and engineering and other fields where we need these tools. So I want to start just by reiterating what statistical inference is. The inference that you are making is that based on looking at a small sample, you are trying to infer what's actually happening in a larger group, which is the population. So sometimes this is literally people, a sample of people from a population of people. Sometimes the word population is being used more metaphorically as an abstract population of hypothetical things that might happen. But in the case of people, you can think, look, I've got this population of 12 people. For practical reasons, I can't find out about all of them, but I can pull out a sample of 4, measure whatever it is that I'm measuring, and again, the inference is, what can I tell about the population from only looking at a sample? So that's the background. A couple of examples. So one common version of this is election polling. So you normally can't poll the entire electorate. You don't even actually know who's going to vote. So the hypothetical population is everybody who will vote in an upcoming election. The sample is the people that you're able to ask, and that you ask them who you're going to vote for, and they tell you, let's say that you observe in your sample that 53% are going to vote for Alice. What you can say about the population is an estimate of what fraction of the population will vote for each candidate, and you also want to quantify the precision of that. So rather than say 53% period, you'd like to say 53%, and based on my methodology, I believe that that might be plus or minus, let's say, 4%. And that plus or minus that you hear when people report poll results is a measure of precision. One of the things we'll talk about today is exactly what that means, what kind of error that includes, and what kinds of errors are not taken into account when people report precision in that way. Just another example to get the space of problems. Let's say that you're doing drug testing. You've got an old drug and a new drug. You have a sample of people that you give each drug to. You have some measure of what the outcomes are. In this case, let's say it's a painkiller. And the old drug, people said 4.1%. And let's see, do I have this right? Other way around, compared to 4.5%. So a couple of things you might want to know. It looks like there's a difference between the two groups. It looks like the old drug and the new drug have different effects. How big is that effect? We would like to quantify the magnitude of the effect. Again, we'd like to talk about precision. So if I tell you that the difference is 0.4 on a pain scale of range of 5, I would want to tell you plus or minus, or I could give you an interval and say there's a 90% chance that the effect size falls in this interval. And I also might want to do a hypothesis test. And this is something like, is there a difference between the drugs? Or is it possible that the apparent difference that we saw in the sample is just because of random sampling, and there's not actually a difference in the general population? So those are the kind of scenarios where we do statistical inference. These are the kinds of questions we would like statistical inference to answer. I've been hinting at some of these definitions. Now let me provide them. Effect size, usually a single number that's meant to quantify how big whatever it is that you're measuring is. You put a range on that, and that can come in the form of a confidence interval or a standard error. So if you see things reported with brackets and two numbers, confidence interval. If you see an estimate plus or minus a standard error, that's usually standard error. They are equivalent to each other. With certain assumptions, you can from one compute the other and vice versa. So it's just a question of which one is more convenient to report. And it also depends on your audience, who's likely to understand which. The other, I mentioned hypothesis testing. Many of you have probably seen p-values as a way of computing the probability of the outcome that you saw under the null hypothesis, which is a way of inferring whether the effect that you saw might have been due to chance. So I just want to get a sense of kind of the background of people coming in. How many people have seen p-values before in the context of hypothesis testing? Okay, that's fine. If you haven't, we're pretty much starting from scratch. If you have, you might have to unlearn some of what you think you know about p-values. So there's that. And how about confidence intervals and standard error? Seen it before? Okay, that's all good. Probably the biggest message that I want to deliver today, if you only remember one thing from this workshop, it is this: that the effect size is by far the most important thing, and if you are only going to report one thing, report effect size. Confidence intervals and standard error provide some additional useful information about precision. And that's a good thing to do, but it's not as important as just telling me how big the thing is. The p-value is by far the least important part of this. Some people go as far as to say that it is completely useless. I'm going to stop just shy of that and say that it is a useful checkbox to avoid a certain kind of error, or at least to warn you if that error is likely. But again, if you only report one of these things, or if you have to leave one out, the p-value is the best thing to leave out. I'll explain why I'm saying this. The reaction that I'm having and that this journal has about banning p-values is based on this problem. Many papers in the sciences will report a p-value as if it's the most important thing, and they often don't report the effect size at all or make it really hard to find. I want to give an example from a couple of years ago that kind of drove me crazy. You see papers like this all the time, or rather newspaper articles like this all the time, where somebody does a study, they find an effect, and they report that there is a difference between two groups. And then that gets picked up in the popular press. They'll say, girls are good at math, but teachers may make them anxious about it. And the effect that they found is that if you score teachers on a math anxiety scale, If your teacher has high math anxiety, you are going to perform a little bit worse on your math tests than if your teacher has low math anxiety. Okay? So I read this, and again, as a quantitative description of the results, qualitative. So they're just telling me in words that there is a difference, but they don't tell me how big it is. So all right, it's just a newspaper. I suppose I shouldn't get upset. Here's some of the language from the article. Girls who had math-anxious teachers were more likely to do worse. And the more anxious a teacher is, the more likely the girls are to pick up on this. Again, these are all qualitative, but they are not quantitative. If you had to put a number on it, so here's an example of a scale that lets you put a number on how much pain you're in. I want to put a number on how big an effect this is. So I went and I found the paper. It was published by the Proceedings of the National Academy of Sciences, which is a highly reputable venue, peer-reviewed, very few papers are accepted. In order to be accepted, they have to be very good quality, and they have to report results that matter, important results. So I crawled through the paper, and I found this, that first of all, there's a regression that connects the outcome, the achievement at the end of the year, with the math teacher's score on a math anxiety scale. And the coefficient is negative 0.21, and it's negative, meaning the more anxiety, the less good the outcome. Okay, good so far. And they tell me that the scale for math anxiety is a scale of 0 to 5, and that the actual measurements were in the range from 1.6 to 4.2. Okay, good. Now, I also found out, now for this one, I had to go into the supplemental materials on the paper. So it wasn't actually in the paper. Oh, sorry, no, this one was in the supplemental materials. Not actually in the paper. I had to go crawling through the web to get this, and combined with that, finally, with that slide, you can finally figure out how big the effect size is. And it works out to be about 0.5 point on a 100-point scale. That is the difference between the least anxious teacher and the most anxious teacher. Okay? That is a somewhat small effect. And it probably doesn't matter at all in practical terms in the real world. Now, I should say it might. Sometimes small effects matter. If we care about fairness, and if any unfairness at all is important, then sometimes small effects matter, but sometimes they don't, and maybe this one does or doesn't. Depends on your point of view. At the very least, you should have that number in front of you so that you can decide whether you think that's an effect that matters or not. The problem is that I had to work really hard to find that number. This is the problem that I want to address. Report the effect size prominently. Everything else is secondary to that. All right, that is my opening rant. I will stop ranting. No, I'm going to come back to ranting later. But first, I want to get you to work. So here's the idea. Download my repository. There should be a file in there that's called effectsize.ipynb. That's the IPython notebook. Launch IPython, open up that notebook, and the way the workshop is going to work, I'm going to talk for a little while, and then you guys are going to work. If you read through the notebook, there are a bunch of cells there that you can read about. They show you some examples, and then there are a couple of exercises. You should go until you get to the point that says stop here. When you get to that point, you should stop. We will regroup, go over what you've seen so far. If you want to go on, you can. If you want to cheat and look at the solutions, you can. There's a file in there that's called, same thing, effectsize_solution.ipynb. Or if you can't get IPython running on your laptop, the solutions are in NB Viewer. And so any web browser, you should be able to click on that link and you can just read through the solutions. And here's now the other piece of this. I do want you to pair up and work with your neighbor. In order to facilitate that, I want to take a couple minutes before you get into this you should introduce yourselves to your neighbor. And I forgot to put a slide in on this, but I want you to do a little icebreaker. To introduce yourself, I want you to talk about what was the first computer that you ever worked on? What was the first programming language that you ever worked in? And what was the stupidest bug that you ever spent a really long time trying to track down? So 2 steps, take a minute to introduce yourselves to your neighbor, and then fire up IPython. Okay, so you've had a couple minutes to get to know each other. Hopefully you are now transitioning into looking at this, this IPython notebook. If you want, you can run the cells one at a time. If you have used IPython before, you're familiar with this, but just if you haven't used it before. So each cell contains a bit of code or the text that I've written. And if you want, you can use shift return to execute each cell one at a time. And the nice thing about that is that you can kind of see the code, and then you see the result, and then you read my text. So that can be a nice way to go through it. The alternative, if you want, the nuisance of that, and this is one of the kind of drawbacks of IPython notebooks, if you accidentally skip a cell and then you continue and you try to execute one of the subsequent cells, it'll sometimes fail because whatever was supposed to happen up here hasn't happened. So to avoid that, simple thing to do is to just select Run All from the Cell menu. Up here, Cell, Run All. And that'll just execute the whole notebook. All the results will be there, and then you can read through it. So either way, as you like, read through, chat with people, ask me questions, and I'll take about 10 minutes to let you go. I'll check in with you and see how far you've got. We'll regroup when you get to the stop here part. I'm going to grab you for just a minute. I got one question about some of the objects that I'm using here. I thought I'd just show you. So the norm function, the norm object, in scipy.stats returns a thing that is a frozen RV, that is RV stands for random variable. What it is an object that represents a probability distribution for a random quantity. In this case, the norm means that it's a normal distribution or a Gaussian distribution. And that object, the RV object, provides a bunch of methods. Again, if you're familiar with IPython, you probably know about tab completion. But this is one of the very nice things about IPython. If you have an object and you say object.tab, it'll give you the list of all the methods that you can invoke on that object. And you can see some of the things that it can do. You can get from it a cumulative distribution function or a probability distribution function. The other thing that you can get from it is a random sample. You can get the mean, median, other moments, and RVS is a random variable sample. So we're going to use that. This abstract normal distribution is like a mathematical entity. It is the normal distribution that has a certain mean and a certain standard deviation. And we talk about it in a stentorian tone. But then you can take a random sample from it, and that's the kind of random sample that we're actually going to work with. Are there other questions that have come up from first contact with the notebook? Okay, we'll take just a couple more minutes and then we'll go over what you've seen. I know not everybody has got to this point yet, but this is a relatively soft stop. There's just one thing I want to point out here, and then you're going to go on. So let me grab you for just a second. What the exercise asks you to do is take this difference in means and report it as a percentage. And if you have things like this that are quantities that have units attached to them, like 15 centimeters, you can't necessarily compare that across different studies. So if I tell you that the difference between men and women is 15 centimeters, but if I tell you that there are two species of beetle and the male beetles are smaller by 0.1 centimeters, we seem to have two very different numbers. I don't know how to compare those to each other. Expressing them in terms of percentages is a possible solution. We could say that men are, in this case, something like 8% taller, and maybe those beetles also differ by 8%. And in that case, we would say that the gender dimorphism in these two species is roughly the same magnitude. So that's a way of conveying effect size in a way that's comparable across different studies. This particular choice is nice because people understand percentages. If I say that two things differ by 10%, we kind of get that. One drawback is that in an example like this, it's not obvious what the denominator should be. So if I say that men are taller by X%, or if I say that women are shorter by X%, it's going to be a slightly different number. In this case, it's not a wildly different number, so it might be okay. There are other examples where it's a very different number. And I would have to make an arbitrary choice that might or might not be the right thing for a given context. So one of the things that we're going to get at is there are many ways to report effect size. None of them are perfect. There are trade-offs. So we've hit one of them. As you go on, you're going to see some of the other alternatives, and we'll talk about pros and cons. So go on. If you haven't got to this point, go ahead and finish up, and then get to the next stop here section. Okay, let me stop you for just a minute. I want to go over the second exercise and introduce Cohen's d, which is the third piece. So I asked about, this is what I call the junior high school dance problem. If I have a bunch of the boys and a bunch of the girls and I match them up at random and make them dance together, what's the probability that I will have the girl taller than the boy? Which of course in junior high school would be a terrible thing if that happened. And I'm using here a list comprehension in Python, so I'm going to zip the male, female, and the male sample and the female sample, just match them up pairwise. The sample is already a random thing, so I don't really have to randomize it. I just pair them up. And then for each x, y, compute the probability that the male x is taller than the female y. And it's been pointed out to me that this is now a count of how many times out of 1,000 the male turns out to be taller, which is 911 out of 1,000. So about 91, 92% is what's unfortunately in this context called the probability of superiority. So that's just what the term is. So the two measurements that we've just described, if you have two distributions and you want to describe to somebody how different these two distributions are, one way to do it is the misclassification rate, which is if you don't know which group somebody is in and you just know their height, would you be able to guess whether they're male or female, how accurately? And you can do that as misclassification, or 1 minus misclassification is accuracy, either way. The nice thing about that is that it's a probability. So it is a unitless number. And again, it's comparable across different studies. So again, if I have my humans and my insects, and I report either misclassification or probability of superiority, that'll be meaningful to you in that context. Okay? So those are the nice things about it. There's one other way of measuring effect size, which is Cohen's d. Again, I've got two distributions. They might overlap to some degree. Cohen's d is a measure of that effect size. I'll give you a couple minutes to read about that. And if you scroll down, you will see an interactive. So here's a static view of the two distributions. In this case, this plot PDF takes as a parameter Cohen's d, which is there are two standard deviations between the mean, and that's what that looks like graphically. So part of the goal here is to get you calibrated so that if you see somebody report d, you'll know what that means. So 2 means this amount of separation between the two distributions, and if the interactive widget is working for you, you should be able to grab the slider and try out different values of d. So that's what 2 looks like. Mine is kind of slow, so it's going slowly. There's what 1 looks like. And so if you read a paper and they say, oh, there's a difference between this group and that group, and Cohen's d is 0.5, then you would have a mental picture of that amount of overlap. And you would realize that 0.5 is a somewhat small effect, that it overlaps by that much. 81% of the distribution overlaps, and the probability of superiority is only 0.61, which is not particularly strong probability. Make sense? Okay, I'm going to give you just a couple minutes to finish up this notebook. Again, I'll come around and help with questions, and then we will move on to the next section. Okay, I got to strike a difficult balance here. It seems like people are doing good work and making progress and asking great questions. I also want to move along and make sure we're getting through topics. I've deliberately, you know how I said that effect size is the most important and everything else is a little bit less important? I've allocated the time accordingly. So we're going to spend a little bit more time on effect size before we go on. We're going to leave this notebook behind for now, but we're going to take a break in a few minutes. So if you want to get back to it, you'll have a chance. To sum up, what I wanted you to get from that notebook is, first of all, if what you're doing is quantifying the difference between two groups, an obvious thing to do is the difference in the means. The drawback is that that number will have units attached to it, and those units make it incomparable across different domains. Relative difference is comparable, but it has the drawback of being asymmetric, and that can be problematic in different domains. We talked about Cohen's d, and that has the property of both being symmetric and standardized. And what I mean by standardized is that when you take a mean, divide by a standard deviation, those two things are in the same units. So their ratio is a dimensionless number. And that's what standardized means in this context. So it's comparable across studies. And given Cohen's d, you can compute other things like probability of superiority and accuracy rates that might be meaningful to you in a particular context. The drawback of Cohen's d is that it is a less familiar number to most people. So if you're a journalist and you're writing in the newspaper, Cohen's d is probably not the best way to convey to the general public. But if you are a scientist, there are a lot of areas in science where people just kind of know what Cohen's d is, like psychology, for example. People who study differences between people, you tell them Cohen's d equals 0.5, they know exactly what you're talking about, partly because they can get calibrated. So the interaction that you just did, I kind of lifted that from this online place where you can slide d back and forth, and it shows it to you graphically, and it computes all of these measures, including two that we didn't talk about, number needed to treat, and Cohen's U, is it U3? U3. I won't talk about those now. So that is all for now about Cohen's d. I want to move on to a different kind of effect. So that was a difference in means between two groups. I want to talk about a difference in proportions now. So I get half the cake, you get a quarter of the cake. That is a difference in proportions. Not the one I'm going to talk about. This one I want to talk about. This is a really interesting study that just came out a few weeks ago. How many people heard about that if kids grow up not eating peanuts, they are more likely to have a peanut allergy than if they grow up just eating peanuts throughout their whole lives? Saw this study? Excellent. Really interesting study. In part, this is an interesting study because the effect size is really big. As medicine and epidemiology goes, this is the biggest effect size I think I've ever seen for an intervention that is as minimal as withholding or giving peanuts. Here is how it got reported on their webpage. It said for the children who avoided peanuts, 17% developed a peanut allergy by the age of 5 years. For people who were randomly assigned, so this is a well-designed study, they were randomly assigned to either eat peanuts or not, only 3% of them, if they ate peanuts, developed a peanut allergy. So the comparison is 3% or 17%. Here's my question for you. How would you summarize this in a single number? If you wanted to report the magnitude of that effect size in a single number, what would you report? And you can think of this in two different ways. Like I said a minute ago, think of yourself as being a journalist. You're going to put a number into the headline. Or think of yourself being a scientist reporting an effect size to your colleagues. The answer was going to be different in two different contexts. Think about it, discuss it with your partner for a minute, and I'll hear some suggestions. Okay, let me hear some suggestions. If you were trying to explain this result to somebody, hey, I just heard about a new peanut study. The difference between kids who eat peanuts and kids who don't is, yes, ratio? Yep. Okay, so a ratio of raw numbers or maybe probabilities. So the 17 divided by the 3? Okay, good, ratio. In that case, a ratio of probabilities. Other possibilities. A percentage difference. So it is, if you give your kid peanuts, you can reduce allergies by such and such a percentage. Or the other way around. Good. Other options. Yes, sir. Good. I like that too. All right, let me look at some of these possibilities. I've run the math on a few of them. Is the joke on the headline that, so this is the actual New York Times at the end of World War I. I don't know. If there's a joke, I missed it. Oh, the number. There is no number. It is just a headline. This is, sorry, yes. This headline has nothing to do with anything other than being a headline. All right. So here's one option that people did not mention, and it's kind of good that you didn't mention it because it's not a great option, but you could just talk about a difference in terms of percentage points. And the nice thing is people kind of get this. There's a 14 percentage point difference between 3 and 14. Okay? And you could express it either way, that either the treatment is eating peanuts and that reduces by 14%, or the treatment is avoiding peanuts and that increases. Either way, percentage points. A drawback of doing this is that when you express a sliding scale of a difference in percentage points, the baseline makes a big difference. So in this example, from 3 to 17%, that's a big deal. But if we're in the middle of a probability range, like 43 to 57, that would be less substantial, especially in like a medical intervention that moves you from 43 to 57. That might be a good thing. It's just not that huge a thing. On the other hand, the flip side of that is if you take something that is a very small risk, like less than 1%, and you turn it into a 14% risk, that would be a monumentally large effect. So percentage points are comprehensible, but not comparable across different points in the scale. The suggestion I got from the back is that you could put things in terms of a percent change. So if the treatment is give your kid peanuts, then you can say, and it will reduce the probability of allergies by 86 or 83%. That is a good thing. That's a nice number. And in fact, many of the newspaper articles about this study, that's the number that they reported. It's not terrible, but this one is funny because it's not clear which one is the treatment and which one is the control. If you put it the other way around, withholding peanuts from your children increases their risk of allergies by 467%. So this is similar to the problem that we had before where it's asymmetric, you have to make an arbitrary choice, and you're leading with a very different number depending on what that choice is. So that's a problem. The other thing is that when you talk about a percent change in percentages, people just get confused. That's a hard thing to talk about. Very common in medicine, and actually I kind of skipped one here. Probability ratio is one option. So I could do the 17 over 3. Probability ratio used to be very commonly used and is now being mostly replaced by odds ratio. Let me explain what odds ratio is, and then I'll explain why. So odds is just another way of expressing a probability. They are equivalent. If you tell me a probability, I can convert it to odds and vice versa. But one form or the other might be more convenient in one domain or another. The reason that odds are so commonly used in the context of betting is that you can do the math in your head to figure out what the payoff is or whether you should make a particular bet or not. In the context of science and mathematics, we more often use probabilities. So if my probabilities are 3% and 17%, the corresponding odds are roughly 3 and roughly 20 percent. Notice that when the probabilities are small, the odds and the probabilities are similar to each other. When you're in the middle of the range, that's not true anymore. And then the odds ratio is the ratio of, let's say, odds with the treatment to the odds without the treatment, or under the control condition. So here's what I would report, and this is what you would see in a medical paper. Most medical papers report odds ratios. And again, depending on whether you talk about treatment or control, you'll get the different odds ratio, but they are inverses of each other. So if somebody reports this, you would just invert it to get that. This is kind of standard practice right now. It's good in the sense that it is comparable across different studies. It's a little bit awkward because of that asymmetry. If you do the math in your head, you will realize that an odds ratio of 6 and an odds ratio of 1/6 that is the exact same effect size. The practical impact of that effect is the same, you're just expressing it differently. However, people being people, see a number like 6 and think, oh, that's a big effect. If you see a number like 0.16, oh, that's not so big. So it's a little tricky. The alternative is the log odds ratio. If you take the log of odds ratio, you have now fixed all the problems. It is symmetric, it is comparable across different studies. There's only one small problem, which is that nobody knows what it means. So in my future world where people know what log odds is, this will be the best thing to use. Anytime, if you are doing mathematics with probabilities, you almost always want to do it on a log odds scale. Let me explain why. Let's say that you want to compute the average between two probabilities. If you just do an arithmetic average between two probabilities, the result is pretty much nonsense. If you do an average between two log odds ratios, the midpoint of that is kind of the meaningful midpoint between the two. If you are estimating a quantity and you put confidence intervals around it, in log odds scale, it will be a symmetric confidence interval where the estimate is in the middle and the endpoints are symmetric around it. So the log odds has lots of nice mathematical properties. The drawback is it's kind of like this axolotl. Nobody knows what it is. It's cute though, but unfamiliar. So just to sum up, here are the 4 different ways. I think of this, there are 2 directions going here. So from left to right, the mathematical properties get better and better, and the familiarity to a general audience gets lower and lower. And that's the trade-off. Again, I mentioned if you're right, if you're a journalist or you're a scientist, your choice along this range is going to be different. So just to summarize where we are so far, effect size is important. You should, when you report it, you should choose the number that is meaningful in context. You should treat the effect size as the most important thing. Standardized measures have the nice property of being comparable across studies, but they are often in conflict with rule number 1. And we should take a break. I think they have coffee out there for us. Let us come back in 10 minutes. I've got 2:32, so I'll resume at 2:42 on my watch. we should get back to it. If you're coming back next couple of slides, I want to introduce the next topic, and then we'll do another IPython notebook. So here's a hypothetical scenario. Let's say that you want to know in the US population, what is the distribution of adult weight? So you come up with this brilliant experimental design. Here's what we're going to do. We're going to get the phone book. We're going to choose a random number out of the phone book. We're going to call it. Whoever answers the phone, we're going to say, how much do you weigh? They're going to tell us how much they weigh. We're going to write it down, and that's going to be our sample of the population. My question. What could go wrong? So again, talk with a partner for a couple minutes. Come up with all the things that are wrong with this experimental design. Okay, talk to me. What are things that could go wrong? Why would your estimate of the adult human population maybe not be a good predictor? Reporting bias, they're not going to report accurately. Yep. You are only reaching people who are listed in the phone book. Yes? And right. So not only is it you're getting a funny collection of people, but the funny collection might be different from the general population in a systematic way. Good. Right, so you could pick a variable like race, and you could see that it is correlated with both the likelihood of answering the phone and with the thing that you're trying to measure. Yes? The heavier you are, the more dishonest. That might be harsh. Maybe you should say, maybe you have more reason that you might want to lie. You might have the same propensity to lie, but more incentive. Men and women might be willing to report differently or round up or down for different reasons. Yep.
The people who are exercising typically don't answer exercising.
Good. All right. So let me see, of the ones that you came up with, let me see how many I came up with. So sampling bias, many of the things that you're pointing out are sampling bias. If things are going well, then the sample should be representative of the population, and that means that anyone in the population should have the same probability of ending up in your sample. And when that's not true, you're sampling some groups more than others, and you might not get what you're trying to measure. So thinking about phones, you might imagine that if you have a lot of people living in the same household, then the chance that any one of them picks up the phone is less than in a household where there's only one person per phone. So you are partly sampling on household size. Maybe very rich people have unlisted numbers or don't have landlines at all. Unemployed people might be more likely to be at home, or exercisers might be more likely to be out running. All of these things are related to both the probability of answering the phone and to the distribution of what the thing that you're trying to measure. So those are examples of sampling bias. Other examples are things of measurement error. So even if your sample is perfectly representative, there are reasons that your measurement might not be right. And that can be, measurement error can be literally an instrument like a ruler and you round off or something like that. But there are other things here that would also be categorized as measurement error. First of all, when you ask someone what they weigh, do you mean with or without clothes? their scale has not been calibrated, they might misremember or misreport, or you might write it down wrong. Or when you take that result and put it into a database and then somebody else pulls it out of the database, they might misinterpret it. And that is actually a real problem with a lot of shared data sets. So one group produces the data set, and then a researcher like me comes along and interprets it. This actually came up. The data that we're going to use comes from the BRFSS, the Behavioral Risk Factor Surveillance Survey. They have adult weights and heights. For the heights, I noticed one kind of weird thing. They're all recorded in centimeters, and there are a surprising number of people in the United States who are 61 centimeters tall. Either that, or there are a lot of people who are 6'1", and that got coded incorrectly. And that turned out to be a real problem for my data because there was not a sharp line that I could put between values that are obviously errors and values that are just short people. And at the tall end, I had a bunch of people who are suspiciously unlikely to be that tall. So that's measurement error. So that's sampling error, measurement error. Random error is the third one. Random error is an inevitable part of a sampling process, which is you might just get unlucky. And let's say that you call 3 people and you just happen to get 3 people who are unusually heavy or unusually light. Your sample, because you didn't measure the entire population, your sample will deviate from the population just because of randomness. So that's the random error component. So here are those 3 pieces. The third one, random error, is the one that is relatively easy to quantify, and that's what we're going to do. The other 2 are hard to measure, and therefore there's a little bit of a temptation and a tendency to ignore them. So this is the second part of my rant for the day, is to remember that there are these 3, and there are more, but these are the big 3. When we quantify uncertainty, we almost always talk about this one. The other 2 are not often quantified, but we need to remember that they are there. So that is the rant for part 2. Your work for part 2, dive into sampling.ipynb, load that up. Same deal, work your way through part 1, get to the part that says stop here. If things aren't working or if you're stuck, feel free to peek at the solutions. And again, Alex and I will come around and help to answer questions. let me interrupt you for just a minute. I want to introduce a couple of the concepts that we need to understand this part, and then I'll let you get back to the exercise. So the fundamental question we're dealing with is the random error part of what I talked about before that says, if I go into the population and I pull out a sample, and then based on that sample, I compute some kind of summary statistic like the mean. So I'm trying to estimate the average weight among adult Americans. I get my sample, I compute the mean of the sample. That number that I get is called a sample statistic. In this case, it's the mean, but it could be other things. Maybe you compute the median of the sample, or the standard deviation, or the 90th percentile, whatever it is. So you take your sample, you boil it down to a single number like the mean. What you'd like to know is how much would that number have varied if I ran this experiment over and over. And the way you do that is by simulating lots of experiments. So in this case, I generate one sample of 1,000 and I compute the mean. Then I generate a different sample of 1,000, compute the mean. And I repeat that over and over and over and accumulate how much it varies, and that distribution is called the sampling distribution of the mean. Okay? And it's how much would the mean vary if I run this experiment over and over. Now, if I remember right, I might have been confusing with the numbers there a second ago. My sample size is 100 in the experiments that you're running. My sample size is always 100. Every time I run the experiment, my sample size is 100. I'm going to run the experiment 1,000 times. So try not to get those two numbers confused. One of them is how big my sample is, how many people I weigh, and the other is just how many times do I run the experiment. The sample size matters a lot. Your results are going to depend on the sample size. How many experiments you simulate is not an important number. That's just what we're using to approximate what the sampling distribution looks like. So if you want to crank that up to 10,000 or whatever it is, it's just either the distribution will get smoother, but other than that, it doesn't matter. All right, so if we take a look at this is the interaction that I suggested. The slider there is the sample size. So if I weigh 100 people and I do it over and over, and each time I do it, I record the mean, well, most of the time I'm going to get something that is pretty close to the actual population mean, which is about 72 kilograms. And that's good. I would like the middle of this distribution to be pretty close to the truth. And what I'm curious about is how much spread there is in this distribution. If my sample size is very large, then this isn't going to vary very much. I'm going to get pretty much the same number every time. If I turn it way down, if my sample size is small, this is a little slow, so it'll take a minute, and you'll see it get wider and wider and wider. So this is what it looks like with a sample size of 10, and it varies a lot more. Now, there are two ways to summarize this sampling distribution. If you want, you could just visualize it. If you take a look at that, you'll say, oh, okay, yeah, normally I'm going to get something like 72, but it might be as low as 60, might be as high as 85, probably won't be too much farther out than that. But if you want, you can compute the standard deviation of this thing. The standard deviation of this thing is called the standard error. It's a measure of the width of this distribution. And you can think of it as most of the numbers are going to be plus or minus 2 standard errors. In fact, 95% of them are going to be plus or minus 2 standard errors. Or if you want, you can make a 95%, oh, I did 90 here. You can do a 90% confidence interval, which is to shave off 5% from this side and 5% from that side, and the middle 90% is the confidence interval. Okay? And either of those are the standard ways to summarize this distribution. And again, as n gets big, this distribution gets nice and small. So with a sample size of 1,000, the precision of my measurement is pretty good. It's going to get down to a standard error of only half a kilogram. So that's the framework, that's the experiment. Now the exercise that you're going to do, This is the sampling distribution of the mean. The nice thing about this computational framework is that you can compute the sampling distribution of any statistic you like. And all you have to do is change the definition of this function, which is called sample stat. So if you modify sample stat to compute the standard deviation or coefficient of variation, min, max, median, percentiles, whatever you want, plug it in, run the interaction again, and you can see how much that measurement varies as a function of sample size. So try that out, and again, we'll come around and answer questions. Okay, I want to show you one version of this that you could do. So I wanted to look at the sampling distribution of the coefficient of variation. So coefficient of variation is a way of measuring the variability in a population in a standardized way. So if I tell you that the standard deviation of adult human weight is 15 kilograms, obviously there's a unit attached to that. If I divide through by the mean, I'm dividing kilograms by kilograms, and I get a dimensionless number that's called the coefficient of variation. Again, the nice thing about these standardized statistics is that they're comparable across different studies. So in this case, I took the sample standard deviation divided by the sample mean. This is actually backwards from what I accidentally put in the notes. It's the other way around, but this is the correct definition of coefficient of variation. And then I fiddled with this a little bit in order to set the range of the x-axis in this graph. So if you did a couple of iterations, if you tried out a statistic, you might want to fiddle with x-lim a little bit. And what I ended up with is this. And what that tells me is that the actual coefficient of variation in my sample is kind of the middle point there. It's something like 0.25. But if I run the experiment over and over, I'm going to see that it varies. And this is how much it varies. And if I change different values of n, let's say n is small, that's going to get wider. The smaller the sample size, the less certain I am about these quantities that I'm trying to estimate. So that's an example there. If you did this with other statistics like the median or the interquartile range and things like that, your number is going to be different, but that behavior, small n, wide distribution, that's going to be pretty consistent. This example is one of the things that I wanted to show you in part to demonstrate the strength of this computational approach to computing these things, which is a big chunk of statistics in the 20th century was about figuring out sampling distributions analytically, doing the math on these things. And for percentiles, and for things like coefficient of variation, which is the ratio of two statistics, those turn out to be very hard to do analytically and turn out to be really easy to do computationally. If you want to swap in a different sample statistic, all you have to do is change the definition of that function and run a few simulations, and you are done. So we just kind of wiped out a good chunk of 20th century statistics by running a loop. And I think that's the end of this section. Yep. Let me recap, and then I'll introduce the next piece. So to summarize, we're going to quantify variability by running simulated experiments. Each experiment, we're going to compute a sample statistic. We get the sampling distribution, and from that, you can compute standard error and confidence intervals. I'm going to talk more in a minute about what confidence intervals mean. Let me come back to it. Sample size increases. These measures of precision get better and better, and we can do this for any kind of variable, any kind of statistic. However, I should say that the example that we just did was a total cheat. That's a cheat code. Because what we started with was a model of the actual population, and we used the actual population to generate our simulated experiments. In reality, you don't ever get to do that, because if you knew the distribution in the actual population, you wouldn't be doing sampling to begin with. You already know the answer. So there is one more step of complication that we have to take care of, and that is the modeling step. The idea here is that you go and you run the experiment, and you get the actual sample. And now from the actual sample, you want to simulate what would happen if you ran the same experiment again. This is a two-step process. You take the actual sample that you collected and you use it to build a model of the population, and then you use the model to generate new hypothetical samples that simulate what would happen if you ran the experiment again. The modeling step is important because you have to make some decisions there. There's not one unique correct model. There are several different ways that you can do it, and they have trade-offs. I'm going to show you one of them. That's what's coming up in the next section. But does the framework make sense? So we're taking away a piece of scaffolding. We don't know the population anymore. We're going to take a sample, generalize it to a model, and then use the model to generate new samples. Okay, go. Okay, I want to look at some code. This is, I believe, the hardest part of the whole workshop. So if you get this, you're over the hump. If you don't, well, there's no hope for you. You're just done. No. So I've taken some of the code from the previous section. I've just wrapped it up in a class. And if you're comfortable with object-oriented programming in Python, this should be no problem. But I know that not everybody is, so hang in there. So I've got this thing that's called a resampler. When you create a new resampler, what you're going to do is you're going to give it the actual sample that you measured. So you run an experiment, you collect a bunch of data, you're going to wrap that data up in a resampler object. The resampler object is going to keep track of what were the actual data, what's the sample size, and then this, I'm just going to use that for displaying things. Don't worry about xlim, not a big deal. But these are the two important ones. This is the actual data and the sample size. Here's the most important function. I'm going to simulate counterfactual, hypothetical future experiments by resampling from the sample, which sounds crazy, but it actually works. And the way I'm going to do it, this is numpy.random.choice, takes the actual data that we saw, and it pulls n values from the sample that were collected. So picture, let's say n is 100. You've got 100 numbers. You're going to choose 100 of them at random. You're going to choose with replacement. That's the replace equals true. What that means is that some values will get selected more than once, other values will not get selected at all, and therefore this new simulated data that you generate will be different from the actual data. In this, some things will be replicated, some won't appear. And if you run this over and over, you will get a whole bunch of simulated experiments. For each simulated experiment, you compute the sample statistic and then collect them. That thing that you get is an estimate of the sampling distribution that we did before by cheating. Except now it's legit. Let me just take a quick look at the rest of the code in this class and see if there was anything else I wanted to tell you about. So compute sample statistics and plot sample stats, those are the same as the functions that we saw in the previous section. I've just taken a function and I've made it into a method that's associated with this class. And if I run this, we can do this. This is the same interaction we were looking at before. Again, this is the sampling distribution of the mean. But the difference is that instead of cheating and using the actual population, now I'm using a sample and I'm resampling from it, and it's pretty much the same, which is good. That's what we wanted. How much sense is all of this making? I kind of tried to sneak up on it one step at a time, but we're kind of done. This is the Megillah of the whole thing. Okay, let me give you a minute to finish up this section, and then we will move on. What you're going to do is create a new version of this. So I gave you a class definition called resampler. You're going to create a new thing called standard deviation resampler. You're going to inherit all the methods that we were just looking at. The only thing you have to change is sample stat. So you're going to override the sample stat that you get from the parent class. You're going to provide a new version that computes the standard deviation, and then run the rest. Give it a shot. As usual, we'll come around for questions. Okay, let's take a look at a solution. We'll wrap up this section and we will get that long promised coffee break. So as I said, I wrote a new class called Standard Deviation Resampler. I inherit everything except that I'm going to override this, and I've just changed it so that it computes standard deviation. Again, this is the nice thing about this framework. What this class does is it encapsulates the resampling framework. All you have to do is plug in the pieces, and you can run this for whatever statistics you like. This is the same code again, and this is what that interaction comes out looking like. I think I haven't actually run this one yet. Good. And again, I can vary n as n gets small. The width of the sampling distribution gets wider. So I got a couple of questions from people that I wanted to repeat. So one of them is, resampling with the same sample size as the original sample seems like a funny thing to do. And people ask, well, what would happen if you resampled with a different sample size? And you can do that. And in fact, that's what this interaction is doing. But it's answering a slightly different question. It's saying, if I run this experiment again with a smaller sample size, how much will the outcome of the experiment vary? And if I run it again with a bigger sample size, how much will it vary? So you can run the resampling process with a different value of n, but you're answering a slightly different question in that case. The other question that I got was, what happens if the sample that you collect turns out to be, just by randomness, a bad sample? It's like way off. And you use that sample to build your model, and then you use that model to generate this. Won't this be hopelessly wrong? And the answer is, yes, it will. If you are unlucky, your sample will be wrong, and therefore your model will be wrong, and therefore your predictions will be wrong. However, it's actually not quite as bad as that. The standard error might be better than the mean. So if you got unlucky and you measured a whole bunch of people who were unusually heavy, then your estimate of the mean might not be very good, but your estimate of how much variability there is in the population might still be okay. But anyway, all of this is based on models. The models can be wrong, and keep that in mind. So let me get to this. So just to summarize, the fundamental idea, yes, sir? Yes, when you drag that slider, it kind of clicks. Yep. Ah. It is less smooth with the standard deviation. Yes, that is generally true. The mean is easier to measure than the standard deviation. And so the jagginess that we're getting, the jagginess is because we're running relatively small sample sizes and a relatively small number of simulated experiments. If you ramp them both up, it will get smoother. But the fact that the standard deviation is jaggier than the mean, we do expect to see that. Good. Let's see. So this is just summarizing where we are so far. One error that you see in a lot of papers is that people might report an estimate plus or minus something, and it's not clear whether that plus or minus is meant to be a standard error or a confidence interval. They are equivalent. Pick one, but whatever you report, just make sure that your reader knows which one you are reporting. Let's do the review questions after the break. Go get some coffee. I've got 3:26. Come back at 3:36, and I will ask you a couple of review questions. All right, back to work, people. While we're waiting for everybody to come back, I have a couple of trivia questions. So that's Frank Zappa on the left. He's my archetype of deviation. And on the right is my archetype of error. Does anybody know who that is? That is Bill Buckner, 1986 World Series Game 6. Still not over it. I remember where I was. Well, payback. Oops, don't want to give you the answers just yet. Difference between standard deviation and standard error. I mentioned this one just because it does make people confused. They are numerically different. That's important to keep track of, but they are just different things. So a standard deviation is a summary statistic that you would use to tell me about a population. And a standard error is a way to tell me about your estimate. So if I want to know how much variability is there in human height, that's a question that's about the population. You would tell me the standard deviation of male height is 7.7 centimeters. And that is a descriptive statistic about a population. Now, if you report an estimate to me and I ask you, how confident are you about that estimate? How much does that estimate vary? That is a measure of standard error. It's a measure of the precision of an estimate. So in this example, in the BRFSS, they sampled 300,000 people. It's a huge sample size. And remember that as sample size gets big, standard error gets small. In this example, the standard error is 0.00034 centimeters. And what that tells you is that because the sample size is so big, if you ran the BRFS again and also measured 300,000 people, the chances are that your estimate of the mean would not change very much. It would change by a very small fraction. I love this example because this is a case where the standard error and the standard deviation are wildly different numbers by several orders of magnitude, which helps you remember that they're just totally different answers to totally different questions. Okay, so that's part one. Part two. I promised to talk about this. So again, this is from the BRFSS. I measure a confidence interval that says, I'm pretty sure that the average adult height for men in the United States is 178.5024 centimeters. And I've reported 7 significant digits there because my confidence interval is so small. My 90% confidence interval said, or 95% says that it's somewhere between 178.5018 and 178.5031. So 5 of those digits I'm pretty confident of. That 6th digit, I'm not sure. So that is an extremely precise estimate. Now, the follow-up question is, it's a 95% confidence interval. What is the probability that the true population mean, meaning if I actually measured every single male adult in the United States and computed their means, and I measure them with extreme accuracy, and I get the correct number, what is the probability that the correct number actually falls in that range? You are all very tempted to say 95%, and you are wrong. There are 2 reasons that you are wrong, and one of them is stupid and one of them is smart. The stupid one is the black hole of statistics. There is the black hole of statistics. In classical frequentist statistics, something like the population mean is not considered to be a random variable. And so you're not allowed to talk about probability with respect to a thing that's a constant. So like Planck's constant, not a random number. And so if someone asks, what's the probability that Planck's constant falls within a particular range, they would say, oh, not a valid question because it either does or it doesn't. There's no 80%. This is stupid. So if you ever find yourself participating in this debate, just back slowly from the room. This is the part that actually matters, and this gets back to where I started. Remember that there were 3 sources of error: sampling bias, measurement error, and random error because of sampling. Okay? We quantified one of them, and what we found is that random error is now the least of your worries. You sampled such a huge sample size that variability due to sampling is extremely small. And what that means is that those other two sources of error will almost certainly dominate random variability. Okay. And so this gets you to the irony, which is that if you do a well-designed experiment with a very large sample size, it is less likely that your CI will contain the true value, which is frustrating but true. But again, it's because one of your sources of error has become so small that the other ones that you didn't quantify almost certainly dominate. And in fact, it is excruciatingly unlikely that we know the average male height with 5 digits of precision. So I would say that the answer to my question, I said here, we don't know. Actually, I would go so far as to say that the probability that the true value falls in that range is epsilon, approximately 0. We would have to be extraordinarily lucky. Okay, so to summarize part 2, which was about quantifying variability, standard error and confidence interval quantify variability. Resampling is a simple and general way to compute it, but don't forget about those other sources of error. This is the break that we just took. So onward to part 3. I left it for last because it is the least important. We have just about the right amount of time for it, so this is good. I'm going to make the claim again that if standard hypothesis testing were wiped off the face of the earth and had never happened, the world would be better off for it. However, you might be curious to know what it's all about, and you might be required to do it, and so I will tell you how to do it. So here's the framework. This is called null hypothesis statistical testing. The logic of this is very similar to doing a proof by contradiction. If you're familiar with mathematics, let's say that I'm trying to prove something about mathematics, some assertion that I'm going to call A. I'm going to do that by temporarily assuming that A is false. And if from that assumption I can derive a contradiction or something that's impossible, I would conclude that, whoops, that's backwards. I would conclude that therefore A must be true. If it's false, bad things happen, therefore it's true. Sorry that I got that backwards on the slide. I will fix that. NHST, null hypothesis significance testing, similar logic. So you go out and you measure something. You see an apparent effect that appears in your sample. The example that we're going to do is one that I measured when my wife and I were expecting our first child. We heard that first babies are more likely to be born late. And then we heard that first babies are more likely to be born early. And these were told to us with equal confidence. So we were very curious to know what the truth was, and I found a data set that's called the National Survey of Family Growth, and they had more than 9,000 participants that they had surveyed, 13,000 births, and so we could measure it. And what I saw is that there is an apparent difference. So first babies and others differ by about 13 hours. And the question is, could that have occurred just because of random sampling, or does that indicate that that difference that I saw in my sample is also true in the population? This is the logic of how I'm going to answer that question. I see an apparent effect. I'm going to assume temporarily that there is no difference between these two groups. I'm going to generate lots of simulated experiments like what we just did, and I'm going to count how often would I see an effect as big as what I saw under the null hypothesis. The null hypothesis is nothing is actually different. Okay? That is the logic of it all. Same deal, fire up the notebook, work your way through hypothesis.ipynb, stop when you get to stop here, and we will go over it. Okay, I want to take a look at a little bit of the code that you're running now, especially if you're familiar with NumPy. There shouldn't be anything too surprising, but I want to point out a couple of things. So this is the null hypothesis. The idea is that if you give me two groups, the null hypothesis is that there is no difference between the two groups. And in that case, I don't care who's in which group. I'm just going to pile them all in together. And the way I'm going to do that is by making a pool where I pool them all together. What HStack does, that stands for horizontal stack. It's going to take two NumPy arrays. So you think of it as an array that has one row and lots of columns, and then another array that has one row, lots and lots of columns. I'm going to stack them horizontally, which is just a complicated way of saying I'm going to concatenate them or join them together into one great big array. And then when I want to run the model, so the null hypothesis is a model of a counterfactual world where there is no difference between these two groups. And now I want to simulate an experiment where I go and I measure, let's see, n first babies and m other babies. And I'm going to do that by taking my pooled distribution and taking a random split. I'm going to split them up randomly by shuffling them and then just selecting out the first n of them and the last m of them. Okay, and this is called a permutation test. The reason is shuffling, the mathematical term for shuffling is permutation. And this is very similar to resampling that we saw in the previous, except that instead of drawing a new sample from the old sample, I'm taking a pooled collection, shuffling, and arbitrarily grouping them into first babies and other babies. Now, in the long run, hang on just one second. In the long run, if I run this experiment over and over, the average difference between the two groups should be 0, because what I'm doing here in my null hypothesis is drawing random samples from the same great big pool. So in the long run, I should get an average that's the same in both groups, and so the difference should be 0. But that's going to vary, and in the same way that last time we ran lots of experiments to see how much it varies, same thing here. Yes. Could we do resampling here? Yes, you could. It is the same thing, and what they are different ways of modeling the population. But the logic is the same. I'm taking a sample, I'm using it to build a model of the population, and then I'm using the model to generate more. And resampling is a way to do that. Permutation is a way to do that. Good question. Okay, I want to give you another couple minutes to work through this code, and then we'll go over more solutions. Okay, it looks like people are making good progress. I want to do a little bit of a summary of where we are. So here are the two concepts that you need to understand in order to grab all of this. The test statistic is whatever the statistic is that measures the effect size that you're trying to measure. So this is very similar to what we talked about at the beginning. In the example that we're talking about of pregnancy length for first babies and others, the test statistic I'm using is just difference in the means. And it's a simple choice. For this kind of stuff, it usually doesn't matter which test statistic you choose. So if you swap in a relative difference or a Cohen's d or anything like that, your p-values are going to come out the same. So usually you can keep the test statistic simple. The null hypothesis, this is a model of a hypothetical world where whatever the effect is, doesn't exist. In this example, it's kind of straightforward to say, look, if I think that the two groups are the same, then I'm just going to lump them together. That's my model. In other cases, it's kind of less obvious to figure out what the null hypothesis is. You have to make some modeling decisions. But if you can model this world, and if you can use it to generate simulated experiments, then you can generate a p-value. In this example, we're doing it by shuffling, so that's called a permutation test. The p-value that you get is the probability that the test statistic under the null hypothesis would exceed what you actually observed. So the number in my example is 13 hours. The difference between first babies and others in this data set was 13 hours. And so the question is, if there's actually nothing going on, the two groups are the same, what would be the chance of seeing an apparent effect as big as that? That's what the p-value is. If the p-value turns out to be small, then you would conclude that what you saw in your sample was unlikely to occur by chance. Okay? And that makes you feel more confident that that effect would also appear in the population, or would also appear if you ran a similar experiment again. Okay? So you compute a probability and then you make an inference based on that probability. I want to go back to the code just to point out a couple of things. So here's the test statistic. If you give me the data, in this case, I'm going to encode the data as a tuple of two groups. So every time you give me these two groups, I'm just going to compute the mean of one, the mean of the other, and the difference is my test statistic. I'm going to run that function once to compute the actual observed effect. So I'm going to run it with the actual data, and then I'm going to run that function 1,000 more times using the simulated data. Okay? So when I run test statistic the first time, I give it the actual group 1 and the actual group 2, and I get that difference, which is 0.078 weeks, which is 13 hours, ballpark. Okay? So you can think of this as being the mark that you have to beat. And the question is now, if I run the model over and over, how often would I beat that mark? So here's run model. We already looked at that. It shuffles the two groups. And the way I've defined these interfaces, I can do this. I can run the model to generate fake data and then immediately take that result and compute the test statistic. So if I run it once, I get 0.081 blah, 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 blah. So that one actually has exceeded the mark. That is bigger. If I run it again, I should get a different number. Oh, okay, that one's small. That one does not exceed the mark. Run it again. Well, okay, small, doesn't exceed the mark. Oh, no, sorry, that's big. I slipped a 0. That one's big. I should get some that are negative. Oh, sorry, no, I will not get any that are negative. This is the absolute value of the difference. Okay, so that's why they're all positive. Some of them are bigger than what I actually saw. Some of them are smaller. So if I now run it 1,000 times and collect all the test statistics, I will have an array that contains 1,000 different hypothetical test statistics under the null hypothesis, and then I plot that. So this is similar to the sampling distribution, except that this is the sampling distribution of the test statistic under the null hypothesis. Just a complicated way of saying I've simulated the experiment and These are the results I get. This vertical gray line is the actual observed effect. That's the 0.078 weeks. And what you see is that actually it is fairly often the case that purely by chance, I could get an apparent effect that's as big as the effect that I actually saw. The proportion turns out to be about 17%. So if I run that, all this does is it just checks how often does the test statistic exceed the actual value that I observed, and it divides by the number of trials that I ran. This is going to vary as I run it over and over because of random numbers, but it ends up being about 0.17. What that means is that if, in fact, there's nothing going on, these two groups are identical, I might see an effect as big as 13 weeks about 17% of the time. And if I flip that logic around, what that means is that the effect that I saw plausibly could be explained just by random variation, which makes me think that it might not be true in the population, and if I ran the experiment again, I might not see the same effect. Make sense? So that's what a p-value is, and what I just said verbally is a way to interpret p-values, is a way to summarize what we have learned by computing a p-value. This is I'm going to tell you about 3 ways to interpret p-values. This is the one that's problematic. You know, I started this by saying that p-values are a problem. I wish they would go away. Part of the reason that they're a problem is this. For a long time in science, if you ran an experiment, you compute a p-value, if it comes out less than 5%, that magic threshold distinguishes between what is called statistically significant and not statistically significant. Below 5%, yay, declare victory, publish, ticker tape parade, 4.9%, we win. 5.1%, oh, terrible, experiment failed, don't publish it. And this is problematic in a whole bunch of ways. One of them is the file drawer problem, which is that all the experiments that people did, if they turned out not to be statistically significant, don't get published, and we don't know that they happened. The only things that get published are the ones that happen to cross this magic threshold, and as a result, the false positive rate could be very high, like 100%. And people have done some meta-analysis to estimate what that actually might be, and the numbers could be 50%. I should have put this in the notes. I'll try to add a link to a paper that came out a few years ago that makes that argument, that estimates, and it says something like most of what we think we know is wrong. And it's partly a result of this problematic way of interpreting things. This is XKCD making fun of the problematic way of interpreting things. Yes, sir? Yep. Yes. Great question. If you've taken classical statistics, you've seen things like t-tests, you know that they're often based on distributional assumptions, like everything has to be normally distributed, or at least the sampling distributions have to be normally distributed. And the question is, for these kinds of resampling methods, are there also assumptions that we're making that are built in? Mostly no. The nice thing about these methods is that they are robust. If the data that you collect are really long-tailed or you have outliers, those outliers will affect the p-values that you compute in the right way. If you have an outlier, your sample error will be big, your confidence error will be big, confidence interval will be big. Mostly it works, with the exception of that modeling step that I described, which is you are always everything that we're doing is based on the idea that you can take a sample and build a model of the population from your sample and then compute these statistics from that model. So to the degree that that model is correct, everything is good. When that model is wrong, there are problems. So it's not a panacea, but it doesn't have the same kind of requirements as the classical tests. The other thing is you don't have to learn 20 different tests. Classical statistics using analytic methods, the analysis tends to be very focused on a particular scenario. And so what you learn is, for this scenario, you need this test, the t-test, the z-test, the Anderson-Darling test, the Kolmogorov-Smirnov test, on and on. What you're losing sight of is the fact that there's really only one test. All hypothesis testing has the same structure. You build a model of the null hypothesis. You simulate that model. You count how often would you exceed the observed effect under the null hypothesis, period. There's no 10 different kinds of tests, and you have to choose which one is right for the scenario. What you do have to do is make a modeling decision, how to model the null hypothesis, and you have to choose a test statistic. But once you've made those choices, the computational framework does all the work. Yes? Yes, that is the one. Good. Okay, so as I said, this is XKCD making fun of the way scientists kind of work. One of the things that is dangerous is what's called the researcher degree of freedom, which is that you, as the designer of experiments, have the ability to tweak things. And if it turns out that you are here on the edge of significance, sometimes you can run a slightly different version of your experiment, a different model or a different test statistic, and get it over the line to 4%. Yay, declare victory. Because of these modeling decisions that I'm talking about, there is no unique objective p-value for any real-world problem. Reasonable people will disagree about modeling decisions and get different p-values as a result. Therefore, most of the time, you should not treat the p-value as having any significant digits. You can think of the p-value as being an order of magnitude. It could be on the order of 1%, 10%, 0.1%, and so on. But forget about reporting 5 significant digits on a p-value. If the order of magnitude is small, then it is unlikely that the effect you're observing is due to chance. And you can infer that it is likely to be in the population and likely to be in another sample from the same population. If it's more than 10%, you can say, look, actually, the random chance thing is quite plausible. And so you probably shouldn't bet anything significant on the outcome of a future experiment. I think anything in between, anything between 1% and 10% is, to me, an inconclusive result. You just don't know whether it's likely to occur in the population or not. When that happens, one alternative is to break out Bayesian methods, which have the nice property of squeezing all the information you can get out of your data and reporting your results in a way that lends itself to decision analysis. So if you're sticking with classical stuff, you kind of have to throw up your hands and say, I don't know. If you use Bayesian methods, you can refine that and say, I don't know, but I can tell you very precisely what I do and do not know. Yes, sir. Yep. Yes, let me see if I can paraphrase that. So you're pointing out that in this case, you believe that the effect is unlikely to be due to chance. In this case, you're suggesting that different choices of the t-statistic might change this p-value quite a lot, and some of them might be considered significant and some might not. Yes, that can be true. In a well-behaved experiment, the choice of the t-statistic should not have a huge effect on the p-value. If it does, that is a hint that your experiment is not very well designed. So in the book, I give some examples where, yeah, you could make some different modeling decisions, or you might choose the difference in the medians instead of the difference in the means, or something like that. You'll get a slightly different p-value, but in that case, it was the difference between 17% and 16%. If it's the difference between 17% and 0.1%, then something strange is going on there. If we have a chance to talk afterwards, I have one example I want to tell you about where that is the case. Okay, so talking a little bit about interpreting p-values, I want to go back into one more setup here and get you to do an exercise. I've done the same thing here with hypothesis test that you saw with the resampler. I've taken all the code from the previous section and put it into an object called hypothesis test that encapsulates the structure of hypothesis testing. The nice thing about this is now if you want to do a different model or a different test statistic, you can just swap in the pieces by overriding methods. So jump into the notebook. We'll work on that for a little bit, and we are sneaking up on the finish line. Let me grab you for a minute. We'll look at some code, and then I'll let you get back to work. So this is the hypothesis test class. It provides the framework for doing hypothesis tests. The structure is very similar to resampler. So when you instantiate one of these objects, you provide the actual data that were observed, and the object is just going to take that data and tuck it away as an instance variable. We're going to use that for some of the other methods. The make model method is useful if you have a little bit of work that you want to do before you start running examples, simulated experiments. You can optimize things a little bit. And then what this does is it takes the actual data, computes whatever your test statistic is and tucks that away as that's the mark to beat that we were talking about before. And then test stats is going to be an array of simulated test statistics from running the model. Here's the loop that we just saw a minute ago. So you're going to run, let's say, 1,000 iterations. Each time you run an iteration, you're going to run the model to generate fake data and then compute the test statistic, which is hard to say, for the fake data and store that in a NumPy array. What the p-value is just how many times does the test statistic exceed the actual value divided by the number of attempts that you made. Okay, that's the p-value. A couple of other methods in here. The maximum test stat is sometimes useful. If you run 1,000 attempts and none of them surpass the mark, you might be curious to know how close you came. And so that's what that's there for. Plot histogram is the histogram that we were looking at a minute ago, which is the distribution of test statistics. And now here's the interesting piece. This is a little bit of Pythonicness that you might not have run into. How many of you from Java-like languages are familiar with abstract classes? You know about abstract classes, abstract methods? This is kind of a Pythonic way of doing an abstract class. What it says is that the parent class here provides the framework. Your job is to fill in the pieces. So you are going to write functions for test statistic, make model, and run model, and they are unimplemented methods. So you don't ever instantiate this class. What you do is you create new child classes that provide those methods and fill them in. And this one is optional. If you don't want to override this one, you don't have to. It just does nothing. The other two are mandatory. If you don't provide these and you try to run this object, it'll raise an exception. Yes? Yes. Sorry, so Python now does have language tools for doing this the right way. You are absolutely right. I'm showing you an old way. Okay. Okay, so now here is a child class that is going to fill in that abstract class. I create a new thing that's called diff means permute. The name is both the test statistic, diff means, and the model that I'm using, permutation. And I'm going to do some different versions of that. I could do diff standard deviation permute, or I could do diff means resample. So I can combine them arbitrarily. But this is the one I'm going to do. So the test statistic is the absolute difference in the means. Make model does that H-stack thing we were looking at before. And run model does the random permutation, the shuffle that we saw before. So this is the same code, just stuffed into a class. Yes, sir? Yes. Yep. Yep. Good question. This looks like an error, but I think it's not. Let's double check it with me. So n is the size of one of my samples. M is the size of the other. When I shuffle the things and split them up, I'm going to select from the beginning to n. So that'll be the first n of them. And then I'm going to select from n to the end. And I think that'll be the remaining m of them. So I think this will do the right thing, even if the two sample sizes are not equal. If m is smaller than n, I think it's still okay. We'll double check, but I think it's okay. So the total length, the H-stack thing, the total length of that is n plus m. Yep, good. Yes, the resampled or the permuted data will have the same shape as the original data. Right, so the make model allows you to do some preparatory work before you run model. The reason is make model gets called once, run model gets run, say, 1,000 times. So if you can pull some of the work out of the loop, it'll be a little bit faster. But you don't have to, you could just do all the loop every time, all the work every time. It does have to be done, yes, it has to be done somewhere. Okay, and so this now is the same test that we ran before with pregnancy length, difference in means, tested by permutation, and the p-value comes out to be about 0.16. Okay, so that's the same as before, and we would declare that that is not statistically significant, that the apparent effect could plausibly be explained by chance. And here's what that distribution looks like. This is the same as what we saw before. Now, I have one last exercise, and you all are being phenomenally durable. Especially, how many of you did a tutorial this morning as well? You guys are good. That is a long day. And walking around the room, I'm hardly seeing any Facebook and email and all that. I'm really impressed that you're hanging in there. I want you to do one last experiment, which exercise. We're going to inherit from diff means permute. So we're going to get everything. The only thing we're going to change is the test statistic. You're going to override test statistics so that instead of computing the absolute difference in the means, you're going to compute the absolute difference in the standard deviations. This is pretty much a cut and paste. Don't overthink it. My point is that in this framework, you can swap in different test statistics, no problem. So work on that, and that is the last exercise for the day. Yes? Good. Let's work on the exercise, look at the results, and then I'm going to answer that question. Okay, so I filled in a new function for test statistic. I just copied the old one, and here where it used to say mean, I changed it to standard deviation. That was all. I can run the same experiment again where I instantiate one of these objects and then ask it to compute a p-value, and the result, the p-value is 0.154. So this says that, yeah, there's a difference in standard deviation between these two groups, but it seems plausible that that difference could happen just by random sampling. So this is another case where it's not statistically significant. But now I think I understand the question I was getting, and I think I misunderstood. So let me come back and try again. If you plug in a different test statistic, you could very well get wildly different p-values. I was just thinking of the wrong thing earlier. This is really just asking two different questions, and the fact that you get two different answers is fine. You're saying, look, there might be no difference in the means between two groups, but there may well be a difference in the standard deviation. One of those could be true, the other could be false, or vice versa. And yeah, you'd get different p-values because you're asking a different question. So sorry for my misunderstanding. I hope it wasn't too confusing. So far, we've run two tests, and it seems like the difference in pregnancy length is not statistically significant. The difference in standard deviation looks like it's not. I decided I had to do at least one test that does turn out to be statistically significant. The difference in birth weight is different for first babies and others. First babies tend to be lighter by about 2 ounces. Again, it doesn't sound like very much. On the other hand, if you are delivering a baby, that might sound like a lot. My second child was 10 pounds, 3 ounces. So 10 pounds, 1 ounce would have been better. Here's the example. I'm using the same hypothesis test object. It's still a difference in means by permutation. The difference is just a different variable. Total weight in pounds is the variable that I'm using, and the p-value turns out to be sort of 0, but I'm going to give you a warning about this in a minute. The actual difference is 0.12 pounds, which I think is like 2 ounces. Sounds about right. And when I ran my random samples from the null hypothesis, the biggest difference I ever saw was 0.09, which is kind of close. And that does suggest that if I ran many more tests, it's possible that I would exceed it, just not very often. And so my caution is when you do this kind of simulation to compute p-values, you should not conclude that p is actually 0. In this case, I made 1,000 attempts, and I never succeeded out of 1,000. So p is probably less than 1 in 1,000. But that's what I should report, something like p less than 0.001. Okay. But to say that p is actually equal to 0 would be to say that the null hypothesis cannot produce this effect ever. And that's usually not the case. It could be, but usually not. So that is the difference in birth weights. If you're curious, just as a quick aside, does anyone have a conjecture about why first babies might be a little bit lighter than subsequent babies? They are born earlier, that is part of it. They are born to younger mothers. There is actually a relationship between birth weight and mother's age. And first babies, on average, are born to younger mothers. So that one is actually a spurious correlation because of a third variable that affects both. But that's getting a little off topic. Okay, let me summarize where we are so far. We've talked about null hypothesis significance tests. What they do for you is help you to rule out one possible explanation. If you see an apparent effect in your sample, one possibility is that it's due to chance. The p-value allows you to cross off one possible source of error. However, it's not the only source of error. So keep in mind these other possibilities. What you see in the sample might be due to sampling bias. It might be because of measurement error. Although in that case, you would have to make an argument for why the measurement error is higher for first babies than others. Now, maybe it's true. You say the length of pregnancy is often based on conjectures of various kinds, and more experienced mothers might get it more accurate than less. I don't know, it's conceivable. Confounding variables like age that I was just talking about. Of course, the other possibility, anytime you read a study, it's possible that the effect is due to an error. Or let's call it politely, let's call it a deliberate error. And in fact, when you read papers, one way to think about what you're doing is you start out uncertain about, look, they're reporting an effect. It might be legit. It might be due to random error, but it might be due to like researcher error. If I've got those three hypotheses, you come along with a low p-value, you've knocked out one of them, but the other two are still on the table. So here's where I come down on all of this is that the p-value does do some work for you, but it's not the most useful piece of work. Here's my summary. The p-value indicates whether an effect might be due to chance, but that's not the only thing you should be worrying about. Okay? The standard error confidence, they quantify error due to random sampling, but that's not the only thing you should be worrying about. And my third point, getting back to where we started this whole thing, effect size is what we actually care about. You should convey the effect size in terms of practical consequences. If you're talking about medicine, tell me about patient outcomes. Education, tell me about how much better the scores are going to be. Don't tell me about p-values. I will stop there. If you will go to this link, you will have a chance to fill out a survey and tell everyone how excellent this tutorial was. Remember, there are 2 L's in excellent. Let me just show you what this looks like. If you click on this, you'll get the page that has our tutorial information on it. And then there's a link there. I just want to show you where that link is. Scroll down a little bit. Here it is, tutorial survey, kind of at the bottom of that page. And if you load that up, there are a few questions, comments. Comments are very helpful for me for improving this for the next time around. In particular, the things I always want to know are pace. Did I give you enough time to work on things? Did I go through things too fast, too slow? And kind of the level of information. I build this as, if I remember right, intermediate Python, no stats. Does that turn out to be true, or do you feel like I lied to you and this was terrible? So take a minute to fill that out if you would, and I will also stick around and answer questions. Actually, you have 2 chances. We can do questions live that everybody will hear, and then I'll stop and you can ask me one-on-one. Any questions that you want to do live? Okay, in that case, I will say thank you very much. It's been great.